So welcome everyone. In this session, I wanted to cover .NET 6 and especially in the context of AWS Lambda and kind of all the new goodies that are coming with it. There's quite a few. I'm really excited to share it. It took me a while to put this together, and so I hope everyone gets value out of it. So even though I'm assuming most individuals on this call will be already familiar with AWS Lambda, I just wanted to establish some common knowledge about it and maybe some details that are important in the work that was done here. Cover some of the enhancements that have been done in .NET 6. There's quite a few that make it just make C# more enjoyable language in the context of .NET 6. There's some compiler features also that are quite interesting, such as source generators for JSON serialization I wanted to cover. And the bulk of the presentation is actually going to be around benchmarking. So it's not just about showing what it looks like, but also showing what is the impact to the performance of your Lambda function when you use what feature, what compiler option, and so on. That was really what I was very curious about. And I just wanted to get an understanding to know, okay, when should I use what? Because there's a lot of tools in our arsenal now. And it's, I think, kind of important to know that we feel comfortable knowing what to use when and where. Quick note about myself, lifelong software guy, love this field. A few years ago, I got the honor of becoming an AWS hero, in part because of these presentations I do, also because of the work on LambdaSharp.net, which was a tool that we built at MindTouch. It's open source. I continue to maintain it. Been in a few companies. I live in San Diego. So if you're a local and you see me at a conference when we can do in-person conferences again, there are more of them now every day. Don't hesitate to say hi and introduce yourself. So let's talk Lambda. I hope by now you have heard of AWS Lambda. It's been introduced a while ago, 8 years, basically forever in context of technology. Though it took them 2 years to add also support for .NET to it. We've been using it more or less since it got introduced in small projects. It's a really, really great way of building business applications, in part because it allows it. You only get billed for code when it runs, and it gets now built in millisecond increments. So it's amazing for low velocity code that doesn't need to be invoked all the time, like cron jobs and so on. It's absolutely perfect. It even works well in more active scenarios, but at some point there is a crossover where running it on Lambda as in a serverless environment becomes more expensive than running it on boxes directly. So that's something to keep in mind. I mean, this flexibility of having code only run when it is needed comes at an increased price tag on what it costs you per CPU cycle. That said, for many scenarios, it's just amazing simply because if something is not being used in your infrastructure, it costs you nothing. It's love it. And so for personal projects, it's definitely the absolute best. But even the business setting, again, you don't have to worry about OS upgrades or anything of that sort, security patches. It's all being taken care of for you. You just ship your code and it gets invoked on an event basis, and that runs. That said, it's important to understand how this kind of works, because there's no free lunch. So when a request comes in, the first thing AWS Lambda infrastructure needs to do is to see, is your function already running? If it isn't, it needs to find a server, download your code to it. It's packaged as a zip file, initialize it, and then it is in a state where it can accept a request, a payload coming in, either from, like I said, a cron job, an API invocation, and then a subsystem that sent an event. That gets deserialized, your code runs, and sends back a response. So these two parts, the init phase and the used, are important to understand. The init phase is free for up to 10 seconds. So you can go to town on it and initialize a lot of data that you need to be before it is able to accept a request. Once the request is accepted from the event, that's when the billing starts. That's on a millisecond basis, and your function can run up to 15 minutes, at which point it gets terminated. Also important to know is that once you return a response, the .NET environment gets frozen. If you had a background thread running, it's also frozen. Nothing happens. As soon as that response goes back and effectively your business logic has concluded, the entire .NET environment is frozen and is only restart as a new request becomes available, and then the billing starts again. but you don't have, the second time around, if the function is already allocated on a machine and the request gets routed to it, you don't have the init phase anymore. This is called a warm invocation. It's much faster, obviously, since it doesn't have to do the whole initialization. But that's the fundamental process. Cold start requires initialization, warm, it's already there, and you can just pick up the right request. Between requests, nothing happens. You can't do anything. There's no such thing as sending back a response and then, hey, no, I'm going to do some cleanup. Never going to happen. Until, of course, the next request, you get thawed, but you don't know if the next request is, or if your Lambda gets descheduled and bye-bye, your code goes. So don't do anything once the request has left. The other thing, the billing is kind of interesting. There's a flat billing, more or less, like million requests, 20 cents. But the rest is actually based on how long your Lambda runs and how much memory you gave it. Something I want to immediately point out is if you target the ARM64 architecture, it is cheaper by 20%. So unless for some reason your code runs a lot faster than x86, ARM is probably the way you want to go. Or you have another limitation, like you're using a native library that only runs on x86, then you have to, of course. But ARM, from a pricing perspective, is the preferred option. And we'll look at some performance data as well that further supports it. So I mentioned that billing is based on time and memory allocated. It turns out that the memory that you give to a Lambda function also defines how fast your code can run. Now, my understanding here, and I have not tested this, so that's why I want to be clear on it, is that you effectively get a full CPU at 1,769 megabytes, or 1.7 gigs. And if you want to take advantage of anything beyond that, your code has to be multi-threaded. Not 100% sure about it, but I don't think if you have single-threaded code and you give it more memory, you actually necessarily run faster. Verify it yourself, but you're certainly going to be running slower under 1.7 gigs. For example, at 832 megabytes, which is half, you get half the CPU performance. The lowest setting you can have is 128 megs, and that's too low. Don't use it. And we'll see that in a moment why as well. There is a really cool tool. I've seen it a lot. I've not used it myself, called Lambda AWS Power Tuning, and it will run your Lambda function on the different memory configurations to give you kind of a sense for how fast it runs. And as you give it more CPU power, but it doesn't run fast because it has I/O latencies that it can't get past anyway, you're just going to start paying more and not get anything. So it's trying to kind of give you that inflection point where you have optimized your performance for what your Lambda needs. That said, for .NET, I always give it 1.7 gigs. If I don't have to think more, again, I'll explain why. But that's for me the usual starting point. If you know you have a lot of I/O latencies, you can probably drop it below. And again, this tool will help you with it. Now, deploying a Lambda, you have a few options. I mean, there's two versions of the .NET runtime that are supported. Both are, and those are the only ones that Amazon will ever support, are the long-term stable LTS versions. There's no .NET 5 because it wasn't LTS. There's .NET Core 3.1 and .NET 6. That's it. So you have those two options. You could do .NET 5 or now sooner, next .NET 7. You do self-contained or containers. I don't cover that here. The other thing, .NET 7 is not meant to be LTS, which probably means, again, you will not be able to run it. So the next expected version that have a supported runtime would be .NET 8, because that's meant to be LTS again. So something to keep in mind. Two architectures, we covered that. And then the memory setting, which goes from 128 megabytes to about 10 gigs in 1 megabyte increments. So you have a lot of ways of tweaking it. Now, remember, this both sets the performance of your Lambda as well as how much memory you have access to. If you exceed that amount of memory, so allocations, again, your Lambda gets immediately terminated. All right, let's quickly cover .NET 6. So that came out in November of last year. So if you're a .NET developer, you probably have already played with it. You may not be using it in production yet. Hopefully this will motivate you to get there sooner. There's a lot of nice enhancement to it. AWS Lambda support only was added in February of this year. So that's fairly recent. And that's when I kind of started doing all my experimentation. And it took me quite a few weeks getting this to run. And again, I'll cover that a little bit. But there's some nice syntactic enhancements that I think make coding much more enjoyable with .NET 6. There's also some compiler capabilities that are quite interesting that I wanted to explore and see what is the impact. And one of them is source generators for JSON serialization. This is a technique that allows you, instead of relying on reflection, to understand what is the structure you expect in your JSON payloads to instead have it generated at compile time. And so it's reflectionless. And it actually shows that it has a nice performance boost. There's also now better support for cross compilation, which makes it easier to build your assemblies in such a way that they can have faster cold starts by using ready to run. Ready to run is a technology that pre-jits the code so that when it starts up, the jitter doesn't have to kick in and do the work before anything executes. And actually has a nice, again, positive impact on reducing the cold start performance or delay. Improve the performance, reduce the delay. Cool. So that's at a high level. I think where it gets interesting is let's look at some actual data on how these pieces fit together and how the methodology was put together to cover this. So there is there's this avoided tool, a module in LambdaSharp, LambdaSharp.Benchmark. And effectively what it does, it will run up to 80 variations of a given project. So you upload the contents of your project as a zip file, just the C# files, the project files, and so on. And then it will compile it for .NET Core 3.1 and .NET 6, if it can. It will also do the tiered compilation option on and off, the ready-to-run option on and off, the different architectures. It will also run it from multiple different memory configurations. I picked 5, the lowest one 128, and the highest one 1.7 gigs, which is a full CPU. It will perform 100 cold starts to get a sense for, to get an average that is more meaningful. I'm sure this could be improved on how the data gets collected. I put an asterisk next to it because some project, it was just running into that 15-minute timeout. So I only did 50 cold starts to get results. And then once a function has had a cold start, it will run 25 times more to get a sense for how fast it's performing and what also the impact is at runtime of tiered compilation, which is an interesting option we'll talk about shortly. So what I'm going to do is I'm going to kind of like review each .NET improvement and what its runtime impact is, if any. So top level statements is a way of writing your code I think in a much more attractive way. So if we take a look at the original style, so this is how you would write, and so you can still write a Lambda function in C# today. So you have your using statements, you declare the JSON serializer you want the runtime to use for deserializing payloads and serializing responses. In this case, it's a little project that's part of the GitHub repo that I'll share the link to later on. I was doing benchmarking system text.json, and it really doesn't do anything. It uses this root class for deserialization and then doesn't return anything. But that's effectively your setup. You declare your JSON serializer, you have a class for which you define the entry point, and then it can take a stream or it can take another type of class, in which case it will use the JSON serializer, invokes it, you apply some business logic, and it returns. Again, here I was curious to benchmark how fast the deserialization goes. So it's minimal in terms of implementation. The new way of doing it looks more like this. So you no longer have a function class that you need to declare. Instead, you are just writing directly statements. So top level statements allow you to, it just looks a lot more natural, like the program starts and it does something. That said, it works a little differently. It uses the custom runtime actually to register it, as opposed to using the entry point being provided by the class and method name, as was the case here, where you basically give it the class name and the method name to call. We don't have a class name or method name anymore. Instead, it just gets the name of the assembly itself and invokes it. And so anything that happens before line 5 is part of your initialization phase. So this is where you can load data sets. This is where you can initialize clients and invoke any code that gets you ready. And then this is where that request registration is effectively done. And in this case, it registers a handler, which is a local function that, again, doesn't do anything, takes a stream request and just returns task completed. Absolutely simple. In this case, the serializer is instantiated and passed in explicitly, as opposed to being done as it was before via this assembly attribute declaration and then the Lambda runtime finds it, initializes it for you, it instantiates it for you, instantiates the function, and then hooks up the method handler. This just looks a lot cleaner to me in terms of flow. It also makes that the whole initialization phase is really everything happening up until this point where you say run async. So a lot less code loss, but because it's not using the original runtime entry point, it does have an impact. So here we have I collected all the data, I put it into a Google spreadsheet. It's actually publicly shared. Again, I'll provide the link afterwards. So you can explore this interactively yourself. So I selected the minimal project, which is in blue, and the minimal top level, which is the one I just showed. So I didn't show the minimal code. It looks very similar to system text.json because it didn't even declare a JSON serializer, and I wanted to cover that. But effectively, it's otherwise the same thing. So what you see here in the top left quadrant is the time it took per cold start for the cold start phase, the initialization phase to be done. And interestingly, the minimal project, so the one in the old notation, is a little slower than the new one. However, that benefit is completely dwarfed as soon as we do the first invocation of that code afterwards. So the handler gets invoked, does something, and in our case, it doesn't return anything, but just that effort of deserializing and so on is considerably greater for that very first cold start invocation. So this is the init phase, and this is the first time that the used phase is happening. On the bottom left, we see the aggregate time of all 25 used phases. So this is not the average per, but the total of all of them, total warm use duration. So used 1, so used 25, which is shown here on the right individually. So you can think of this as the area underneath these lines. And the difference is so small. This could have just been a sampling error. Like, as you can see, every once in a while it jumps. Doesn't matter if you use tiered compilation or not, which tends to be more likely that there will be jumps. You just have these inconsistencies. There's just latency being introduced somewhere sometimes, and they're outliers, and currently they're not being filtered out. But this is close enough that I would consider to be of identical performance. So it's a little faster here, it's quite a bit slower there. Doing the cold start, it's not really huge. Then again, if you're optimizing for cold start, it's something to remember that top level statements, nice annotation, has a little bit of an impact on that very first invocation. Now the other thing which I love with the new top level statements is .NET 6 also introduced the concept of minimal APIs. And this just works gloriously nice. All you have to do, it works exactly the way everything used to work before. And you just add this one. So if you've used minimal APIs, if you haven't, check it out. Very nice addition to .NET 6. You basically just say, hey, I want this to be able to be hosted inside AWS Lambda environment. This is what I expect my payload to be packaged in. There's REST API, HTTP API, and I think one more. And that's just the way Lambda gets the request inside an outer envelope so it knows how to deserialize it properly. You build your app, you hook up your various handlers, and then just say run, and off you go. And this works nice. It's definitely a style I could see myself easily adopting, going from the previous one to something more like this for handlers. So we'll revisit a minimal API in a moment on performance, but first I wanted to talk a little bit about the AWS Lambda configuration settings as well. And it's .NET 6 is labeled as the fastest .NET ever. It's not entirely true, at least for when it comes to Lambda. I don't know why, but there is quite a difference in performance between the startup time for .NET 6 and .NET Core 3.1. So here we have the system text JSON project. So that's the one you saw the code for earlier, and compiled for ARM64 and x86-64. It's using tiered compilation, it's using ready to run, and it's using 1.769 megabytes of memory. Those are all the same for the project. So the first two bars are the ARM64 version, the x86 version running on .NET 6. The next two are the same, again, ARM, x86, running on .NET Core 3.1. And you can see that the code initialization phase is considerably shorter on .NET Core 3.1. I mean, this is, if you look at other results we had earlier, we were talking about 20 milliseconds difference or so. This is 80 milliseconds. So definitely noticeable. Similarly, the code initialization, for some reason, it's always faster. So this is the .NET 6 version. This is the .NET Core 3.1 version, and it's faster on ARM64 as well. And then this is .NET 6, .NET Core 3.1 on x86. And again, not as noticeable when we're talking about 20 milliseconds. So now we're more in the domain where there could be some noise in the data sampling. But .NET Core 3.1 is faster at starting up, period. There's no doubt about it. This was run over 100 times. For averaging it out, well, it was 100, well, not over, it was run exactly 100 times, then averaged out. And so I was very surprised by this. I thought .NET 6 was going to be faster across the board. It is not in this case. However, it is faster on a per invocation. Once the function is warm, and we look at the data here in the bottom left, we can see that we shaved off about 5 milliseconds or so. You know, maybe here's 12 milliseconds. But remember, this is the total of 25 invocations. So it's half a millisecond per invocation. That is not a massive improvement. I would consider this to be, it's close to the noise level. So again, something to make note of. Target .NET 6. I would target .NET 6 for every project unless for some reason I really cared about cold start. Now I'm going to again caveat that you may not want to care about cold starts. And this will be a recurring theme. Now, the other big one is, of course, what about the performance difference between ARM64 and the x86 architecture? So ARM64, as you saw earlier, is 20% cheaper out of the gate, which means that unless x86 is significantly faster, you're probably it's gonna be cheaper to use ARM64, and that kind of bears true. So here we have the sample AWS Newton top level. So that's a top level version, but using the Newton serializer. This is in the text serializer, and then the minimal API that I showed. So these are the three projects. They're all compiled on ARM64 here in the first 3 columns, and then they're compiled using x86 64-bit, the following 3. And so you can see that the ARM version is a little bit slower as we kind of jump across. These are really, really close, but not a whole lot. Certainly not sufficient to make up for the price advantage. Here, the first cold initialization, again, there is x86 is faster. So something to keep in mind, again, if you really care about cold starts. But after that, well, no, still, sorry, I was comparing these two. 5 milliseconds. These are virtually, let's see this. No, this is, yeah. Although this might have just been, this seems a little bit of an outlier. So the red spiking really a lot here. So it might have just that was a little bit noisy. And then these two are completely identical. So this is the minimal API processing, and makes no difference if you're on ARM64 or x86. So cost-wise, this is pretty simple. I mean, you should definitely consider using ARM64 if you can. You get a built-in cost saving, hits you a little bit on the cold start side, but after that, you're fine. So I would definitely make that my recommendation for most cases, unless, again, cold start is important to you. Now, memory, unfortunately, these were not sorted properly. So it's not from lowest to highest as I would have liked it to be. Instead, it's 1 gigabyte, 128 megabytes, 1.7 gigs, 256, and then 512. So we're just going to have to unscramble the data a little bit. But here's something that's really important and to keep it absolutely in mind. Whereas the other graphs go all over the place, you will notice that the init duration, they're all identical. And there's a reason for that. Because during that init phase, so where your code is warming up and getting ready for that first request, that first payload to come in, AWS Lambda will automatically run it at full speed. Everybody, doesn't matter what you gave it for memory. The throttling only happens after that request comes in. Then you run at the speed corresponding to how much memory you give it. But up until that point, it is full speed, probably to make the call start as short as possible. It's just an assumption on my part. But it's absolutely evident here that the code they're all running at the same speed. Then, then you get your payload. And remember, this is the minimal API sample. And if you starved your code with only 128 megabytes of memory, you'll pay the price for it. I mean, this went from the optimal case of 167 milliseconds to 2,594. That's a really big jump. I mean, you just giving it twice as much memory, or it drops it by half, and so on and so forth. I mean, according to this, I would not go under a gig. Gig is probably fine, but anything after, I mean, you're just really penalizing yourself in performance. Again, you could argue if you do a lot of I/O and you're waiting on other systems, why pay for the time that your Lambda function is waiting for a response from another service it's calling? Because you're active, so you're going to get billed for it. So that's probably where that the tuning tool comes in, and you can kind of find like, okay, how much memory should I give it so that it's basically more memory doesn't add more, and removing removing memory makes it significantly slow, and you can kind of identify that break-even point that way. The slowness is not just in the cold start and the first initialization; it just carries through all the way. That said, in the 1 gigabyte versus 1.7 gigabyte, again, this is over 25 iterations. You do see it's almost identical. So giving it actually quite a bit more memory and therefore more performance didn't make a whole lot of difference here. So 1 gig is probably not a bad starting point for a lot of projects. And this is, of course, the per iteration, again, dominated by the red. But yes, do not use 128. Yeah, I don't know how much more I can say about it. Okay, let's talk about JSON serialization. This is one I was really excited about. If you haven't ever played around between system text.json and Newton soft JSON.NET, it performs significantly differently on Lambda. I mean, Newton soft is a big assembly. There's a lot of jitting going on. It takes a while to initialize. However, it has been the standard for many, many years. Many libraries are configured for it. The reality is, unless you have full control over the code base, you may have to use it. It's super feature rich. I mean, it is the golden standard in what you can do, but it is big, and we'll see that in the graphs quickly. And of course, it relies on reflection, as does system text.json. In .NET 6, system text.json has made a lot of progress. Some of the features that were missing, like serializing of fields and so on, have been added. And it's not an additional assembly anymore. It's part of the runtime. So it reduces your package size, and it's quite fast. I mean, it's definitely my go-to serialization solution. It still relies on reflection. And then you have source generators. The latest toy in your tool belt. I say toy because unless you know exactly what you're doing, you may want to stay away from it. It's awesome that it does not use reflection and that it is done at compile time. That is a huge plus, but it does miss some big features. The one that I just astonished wasn't there is no support for JSON converters. So converting data types cannot be registered. So if you have something that and you did not annotate the class properly, there's no hope of getting the source generator to work. It's probably going to get added in .NET 7, I'm going to guess. I think this is very similar to the first version of system text.json, where Microsoft just wanted to ship it, get some community feedback, and then improve the next version. I think fast iterations like that is the right way of doing it, but it means that this V1 of source generators is very limited, and it has some bugs. Case in point, actually, because this one really got me good. Let me quickly show you. So I was pointing out that we're doing. So this is the repository where all the projects are. I don't need this guy. So this is where all the types, I wanted a big fat payload to deserialize. So it was important for me that if I'm testing JSON serialization performance, it better be a nice big class. So this is, you see it in the right here. This was generated by taking the GitHub pull request API JSON sample and then running it to another tool that created the C# version of it that then could be used for deserialization. Now, what I'm looking for is this line here. What it generated wasn't this. It generated, which is perfectly valid, it generated this, saying that, hey, base is a keyword, and therefore you can just use that. You have to put the @ symbol in front of it. Perfectly fine. Source generators generated invalid code, which then broke compilation, and just, I was really surprised. The only way around it was, as you can see here, I changed the name, and then I told you know what, this should really be called base. It's just, I can't say @base because you break. So again, beware, there are some rough edges on source generators, in addition to missing features. So in terms of using them, it's not that different. It's all, from the regular generators. I mean, you now have to declare a source generator Lambda JSON serializer instead of default JSON serializer. And then you give it the serialization context class, which is a partial class you define that derives from the JSON serializer context. And on it, you use class attributes to specify which types you want to be able to deserialize, serialize or deserialize. And because it's a partial class, the compiler can now create additional method definitions that correspond to these attributes at compile time, make it part of it, and make it available. So these are kind of like the two changes you have to do to adopt source generators. But you have to have full control over these definitions, so you can basically circumvent the limitations and also any kind of issues, like I said, like the attribute. Here I'm just highlighting, this is the new notation for file scope namespaces, also really nice, avoids you to have to indent everything. Loved it, converted immediately every single .NET project I had to use this notation. Again, just cleans it up. I really like what they did in terms of making C# more pleasant to use in .NET 6. Compile improvements there. So that's how that works. And so let's take a look. So these are now the three serializers I mentioned: Newtonsoft, system.text.json, and actually in the order, Newtonsoft is blue, source generator is red, and then system.text.json is yellow. Initialization-wise, it's close enough that this could again be a sampling error. I would expect this order though to be somewhat there. Newtonsoft is a bigger library that's part of this deployment. Source generator has more code to deploy. And then system.text.json does not require anything additional, so it would make sense that it would be slightly smaller and therefore faster to deploy. First iteration though, Newtonsoft initialization is slow. I remember noticing this years ago, and it absolutely was flabbergasted. I mean, this time, whoops, is just Newtonsoft getting up and getting ready for work. I have no idea what's happening in the background. Probably a lot of initialization, but it is definitely. Remember, these are 1.7 gigs, right? This is basically full CPU speed. Source generators, on the other hand, are super fast. I mean, you still need the code jitting, but you don't need to do any of the reflection and data structure buildup that happens with the reflection-based methods. System.text.json is a great middle ground. It is, I think, for most projects, feature-rich enough that I would recommend just targeting it and not Newtonsoft. If you have control, I would highly recommend avoid Newtonsoft and just go with system.text.json. If you have enough, if you have full control, try source generators, but make sure that you have good code coverage with testing, because I don't fully trust it. The fact that I run into this issue, the surprises with the lack of converters being there. Yeah. Anyway, once it's up and running, Newton and system text performed at the same speed pretty much, and source generators have a slight edge. Over 25 iteration, again, we're talking about 5 milliseconds, so it's a very, very small edge, but it's there. But yeah, source generators, interesting new beast. So just try it out, but be careful. Now, This is probably the one that gave me the most headaches. And I'm going to share with you what I learned and what I recommend. But I also will recommend that you do your own experimentation for your own code, because it was a little bit, it wasn't cut and dry. It wasn't black and white, just clear, and they're like, oh yes, this is always good. It really will be situationally dependent. So there's two features I wanted to test out in the compiler. Ready to run, which is this ability of generating code, pre-jitting code ahead of time. You have to tell it which architecture, is it x86, ARM64. You have to, of course, tell it that it's for Linux, or well, you wouldn't say anything else. Linux is the only one that you can target for Amazon Lambda. So you provide that with these options. It would be x64 if you go on Intel instruction set, or ARM64 otherwise, and then you say you're passing this property, and it will make your zip package larger because more code is in it. If for some reason you targeted 64, ARM64, but it gets deployed in x86, it will just ignore that part and reject it. So you don't get the benefit, but you get the penalty of the larger package. Tiered compilation, I have a lot more reading up to do. So tiered compilation idea is, hey, let's do really a quick and dirty job at generating code, jitting code, so that we just get things up and running. And then as code gets invoked more frequently, let's rejit it. Let's replace it on the stack. Let's do some additional effort to make it more performant, but taking a little bit more time, analyzing things a little bit more, and rewriting it. That means that by the nature of tiered compilation, you will see bumps along the way as your Lambda function is warm, and it will not be as consistent. Still reading up on tiered compilation, but it looks like it's the first 100 milliseconds or so where it does most of its work. 25 invocations, no, 50 invocations of functions. I have to confirm those numbers, but I'll provide the links to the specification for tiered compilation. Again, what it does mean is that it messes with code that has been jitted, and therefore it will have an impact. That is important to understand, because it might have consequences on how much memory you give your Lambda function in order to compensate for the additional effort that jitter has to do to rejit things at runtime. So here are the results. So I used again the sample minimal API project, just targeting ARM64, just doing .NET 6. And we have the 4 variations here. The first one is no tiered compilation, no ready to run. The second one is no tiered compilation with ready to run, and then only tiered compilation, and then tiered compilation and ready to run. So those are the 4 columns. And you can see how just enabling ready to run gave us a little boost. Just enabling tiered compilation gave us also a nice boost, but they're not quite additive. It's not like the final version is really the benefit of both combined. It's a little less, but still it is definitely the fastest. Similarly, doing that first invocation where the jitter has to do most of the work, we find that having both options, tiered compilation and ready to run enabled, gives us a nice improvement here on that very first one, right? Because it's able to just spit out some code quickly and then revisit it later on. So for cold start scenarios, this is very attractive. But like I said, this comes at a cost. When you look at the bottom left graph, you can see that when we did not use tiered compilation, so this is ready to run, this is nothing. These are considerably faster, well, 15 milliseconds between these two. I mean, so we shave the millisecond off, let's say, than the tiered compilation version, because the tiered compilation is going to keep messing with your invocation. And this is not light messing. I mean, it is rewriting the stack frames and so on, so that it can replace the implementation of that function method that it has identified needed to be rejitted. And I mean, the fact that they can pull it off is super cool, but it does mean instead of having a nice steady state performance, you're going to get this humps, and you're not going to get optimal performance until later. If your Lambda function lives long enough, it should converge exactly on where the other ones are, and you got that other benefit. But in those early warm invocations, you're going to get hit. It's unavoidable because it has to figure out what it needs to rewrite. The other thing I wanted to point out here, you notice that this first, I don't know why my mouse is doing that, pardon me. This very first use, this is a warm invocation. This is not a cold. The cold invocations are up here, the one where it never got run before. The first warm invocation is always much slower than the follow one. I have no idea why. That is something I'd like to dive into, but just be aware, the even though this function, Lambda function, was now warm, the next time it got invoked in warm, it was still having this hiccup. And it doesn't matter if you have TIT compilation on or off. As you can see, you always have it and then it settles. I have no idea what's going on, but it isn't until subsequent iterations that you really actually get good performance. A mystery that deserves to be researched further, but I haven't figured it out yet. Just be aware of it. This one is an easy one. There's actually no performance. I love this. This is just a language improvement. If you have written a lot of .NET code for, C# code, pardon me, I don't want to offend F# or VB users. So if you've written a lot of C# code, you always had to say like new list object v2 request, and then you could populate the parameters. You can omit that now. You just say new parentheses open close. It knows what the type is here based on the signature of this method, and off you go. It just shrinks all the code typing and so on. I don't love target type new expressions for everything, but for that one, I love it. It really cleans up the code very nicely. So looks like I'm actually made it more or less on time. I just want to kind of like summarize. There's a lot of information that I threw at you, and hopefully it will help you kind of make some of these choices for your own projects. Use ARM64 unless you have a really good reason not to use it. It seems like the no-brainer choice. It's 20% cheaper out of the gate, has the same performance as x86, is sometimes faster. I would make that my default, would be my recommendation. If you need to optimize your code for cold starts, again, stress, big if, pardon me, then TIT compilation ready to run are definitely your friends. I mean, they bring it down. You push off the cost to later invocations, but eventually that will catch up. I mean, it should converge back after more invocations on the same performance. You may also want to consider using .NET Core 3.1. It also has ready to run and TIT compilation support. It is fast at cold start, period. There's no way around it. x86 was a little faster in cold start, oddly enough, but then slower in warm invocations. Again, another mystery of life. And then, yeah, don't use top-level statements because they rely on this custom runtime support mechanism. And I don't know why, but it seems to be quite a bit slower than the default one, the original one that has always been there, where it instantiates your class and then calls your method. Give it enough memory. That's a big one. Again, depending on how much IO you do. And then the last statement is really, maybe cold starts aren't the big bad wolf. At least I have always made them out of it. I've always had this quest of, let's make cold start as fast as possible. This is one of the reasons I did all this benchmarking. But by moving your initialization into that init phase before your request handler gets registered, you get up to 10 seconds of free time. And I tested it. I don't think I pasted it back in here, but just to bring it, here's the test that I run, just to make absolutely certain I wasn't saying something totally wrong that would cost you dearly. This is the code I showed earlier, using statements. Here's where we register the handler. This is what makes it possible for our code to get this request. Everything up till that point is init code. So to make sure that it worked as expected, I did this little thing. And you can then look in your CloudWatch logs. It will show, hey, init took 5 seconds. Your code afterwards took 200 milliseconds because it was cold, had to initialize all this stuff, and you were billed for 200 milliseconds. Those 5 seconds, you did not get billed for. You can write, I would just initialize all the clients. I mean, initializing AWS clients is also not super fast. They're quite bulky. So initialize everything up front before you register your handler, and that initialization is free. Beware though, obviously, if this is on an API request, this is where calls are important. But if you're just listening to an SQS queue or an event bridge event or anything else that is fully asynchronous processing, who cares? Just do it there. Don't pay for it. This is probably going to revoke my AWS hero status. Okay, so here's some links. I'll put those in an email, since obviously you can not click here, to the tuning function. I'll also put them. I'll make the presentation also available. It also points to the LambdaSharp.Benchmark project if you want to see how that was done with the whole the code build and step function to run all these experiments. Or heck, if you want to use it for your own projects, as well as and that one I should probably show the LambdaSharp Explorer. This I wish I could. I tried rebuilding it with QuickSight, but it wasn't successful. So all the data that got generated, the CSV has I have it in this this sheet here, where it has basically the timings, and then again this is publicly shared. Here you can then select which project you want to visualize. For example, AWS SDK versus, let's say, minimal top level, and then it shows you the differences. You can then also say if you want to see it maybe without TIT compilation, without ready to run. Oops. For all architectures, maybe just care about ARM64, and then but you won't care about .NET. So, for example, now we can see it. So this is where the graphics were done. So it's fully interactive. So if you want to explore the data that I presented and maybe some other scenarios that I did not cover, you can cut and slice the data this way and then visualize it and just get a sense for what it looks like. So my little window is in the way, and loading. Here we go. So you can reach me at LambdaSharp. LambdaSharp.net is where the LambdaSharp code base is, and then LambdaSharp.Benchmark on GitHub is all the code, all the sample code that was profiled, as well as the benchmarking harness that I wrote for this is fully available there, and open source. So hope you found it interesting, and yeah, let me know if there were other questions you would like me to answer.